Okay, we are recording. So today's it's kind of Fourier Revisited, but it's a lot of applications and tying things together. All right, but before we do that, I need to talk a little bit about the what is it? Homework 12, the current homework. So this is going to be something you're maybe not quite used to, and that's okay. All right, this is a inverting Schmidt trigger. All right, now notice that the feedback network here is coming into the positive node. All right, so let's draw this op amp out where we have the summing block. We have V in like normal, right? But it's minus. Before, we've always had it positive, right? Then we'll have a transfer function, and there's a variety of transfer functions. And then we'll have our feedback network, and we'll call that beta, because looking at it with these resistors, ideally, there's no frequency component. If there was, we'd call it G of S. All right. So now, right, we have to look at things like just a little bit differently, all right, where V out will now equal minus V in H of S, and then it will also equal V out beta positive H of S, right? Then we'll bring the things that scale V out. Here, okay? And then we can find the transfer function. All right. Now, again, this Schmidt trigger, which I'll explain in a little bit, right, operates on positive feedback. And if you don't actually use a model, at least the integrator model, it won't work. If you were to analyze this circuit with everything ideal, right, no delay, no capacitor on the inside, you would get minus V in times 1 plus R2 divided by R1. And it's not, but that's not true. All right. This circuit, if it's above a certain threshold, will go to the negative rail. If it's above, it'll go the opposite way. All right. So in order to truly understand this circuit, you have to have something like this. If I put AVO as a constant, I'll get an answer, but it won't be the right answer. So this is the simplest thing to do. So we'll substitute that in, right? I'm not going to show every step. All right. But we can see now that it is inverting. All right. So that just means it's going in the opposite direction compared to before. But notice we have minus beta AV, right? And so when we take the inverse Laplace of that, right, we're going to get which is doing that in time, right? But at some point, it hits minus VDD, right? And it can't go any more negative, right? So, and so why is that useful? Is that if I look at V in versus V out, okay, that if I go V in versus V out one direction, this is my transfer function. But if I start high and go low, this is my direction. And what that's saying is if V out is low and you go past this threshold, the output goes high. But then if you're bouncing around, it won't go low until it goes past that other threshold. All right. So it gets rid of noise. And actually, if you saw that manual I sent about these TA opportunities, we're actually using the Schmidt trigger as a stochastic resonator, which is a whole other topic. All right. Now that's one way. And there's another form, and it's called the non-inverting Schmidt trigger, right? Now, this one, you might be a little bit tricky to get at first because it doesn't lend itself immediately to what we're doing. But that input on the negative side, it's just tied to ground, so it's not there at all, right? Now, sure, we're going to have a transfer function, and we're going to have a V out, but the confusing part here is that the in and the V out are kind of all connected on the same resistor network, right? But even though V out depends on V in, it's still a voltage source, and we can still use superposition, right? So that Vx, right, Vx due to the input, right? Well, then you just short the output, and it's just voltage division. Oops, that should be 2. And you get R2, R1 plus R2. So that's how we get the input in, right? And we can just call that alpha, right? And then here, this would just be, for superposition, we would short V in, which of course means V out is 0, but superposition's a, kind of a linear trick, right? Vx due to out is voltage division the other way, And we've been using beta for that, right? And again, it's added. So now, right, what is V out? V out equals V in alpha H of S, right? But it's also equal to V out times beta times H of S. And when we find the transfer function of that, okay, we get okay. Now in this case, we don't ever say, oh, if this is bigger than this, it goes to a DC and we get some transfer function like that. No, this doesn't work unless we keep this here, right? Because it's just, again, we're using positive feedback. We're putting, oops, yeah, I'm sure you're probably saying, what's that plus sign doing there? It's minus. Thanks. This is an out of control system that we're using. So that should be enough to answer one of the questions on the homework. Some of the other questions on the homework aren't strictly related to transient system identification. They're like review to help you get going on for the final. All right. But that should get you started. All right.
Professor?
Yes.
Question. So what is the meaning of positive feedback or negative feedback?
Okay, good question. Is that so positive and negative feedback? It's really, you have the feedback and how's it coming in? So I have our V in, I have some transfer function, right, out. Now I'm taking this and I'm bringing it back in. Okay. Well, if I'm subtracting it, it's negative feedback. So I'm adding back, I'm subtracting some of the output times some transfer function, and I'm subtracting it. All right. Positive feedback would be there's a positive symbol there. Okay. Now, usually, right, when we talk about positive feedback, we kind of think that that's a good thing, right? But in electrical engineering, usually that means your system is out of control, right? So, what can happen in a financial market is there's a stock or some mortgage-backed security that people think is good, right? And so then people buy it, but then, and that raises the price a bit. And then people now think it's a good investment. So more people buy it, which then raises the price again. And so then more people buy it, and then that raises, and the more the higher the price goes, the more people try to get into it, right? But of course, what can happen is if it's overvalued, it can come crashing down, right? Which is nonlinear, so therefore it's not part of 110, right? But positive feedback is when you do something, you get kind of more of it, right? Negative feedback is if you do something, you kind of get a little bit less. And a system in control, right, will always go to a fixed value. All right. Does that help?
Yeah, thanks.
Okay. Somebody gave me a mug that said, I only give negative feedback. And you can laugh or not laugh if you I won't make you laugh, but I've still got the mug. Yeah. Yeah, Dogecoin, or I think I'm saying that wrong. But yeah,
Well, I didn't catch that.
basically there's a cryptocurrency, right, that has gone through the roof,
I see.
Dogecoin, and it's just, I mean, a currency, you're supposed to buy things with it, right? And yeah, people trade in dollars versus other currencies. Things are up and down, and you can make money that way. But this is so crazy. There's nothing to it. And not only that, but even to buy something with the cryptocurrency costs a lot of energy just to transfer it. All right. So there's some real problems with there. And then there's another question. Is positive feedback and frequency bad? Well, here's the thing. For the Schmidt trigger, it's great because it's a really effective way of getting rid of noise. Okay. And yeah, having a pole on the right-hand side just means you're out of control, but you might want that. Okay. You could have complex poles right on the real, where the real part is equal to 0, because you're trying to make an oscillator, right? It doesn't usually connotate good or bad. It's just, unless you're trying for one and you get the other, right? So if you're flying an airplane and something goes wrong and it becomes out of control, well, that I'm going to say is bad. Okay. All right. So these notes here are in Canvas under notes, but there's some things here I've looked, and how to say, they're not helpful. And I think I just forgot to remove them. Okay. So the things here are probably more helpful on these notes. All right. Let's make those bigger. All right. So we have some things on the Fourier applied to the pulse width modulator DAC and the Butterworth filter, and some poles and zeros and what things look like. All right. Just got to see which one I want. Okay. So, when I first started teaching this, it seemed, why do we have two ways of looking at the signal? When in fact, they almost seem to be the same kind of transform, right? One, it's a complex number, which means you can have a real part, and it's done on a two-dimensional plane. And then the signals can be at 0, or the signals don't have to exist for all time. On the other hand, if a signal is always existing, right, then, and you're only on the imaginary axis, you can use a Fourier. All right. And it really boils down to this: is it like if we didn't do the Fourier analysis and the pulse width modulated DAC, you might just think, oh, set S equal to J omega, and you can do your Bode plot. And that really is kind of what happens, right? But it's actually, by breaking up a signal into its sines and cosines, you can do some things that you can't do in Laplace. And one of them is this pulse width modulated DAC. All right, which you should be familiar with by now from 110 lab. So pulse width modulated signals, right? They have a DC and AC component. And what are we modulating? Well, right, this is a 50% duty cycle wave, right? But if I make it, you know, a tenth of 10% or 1% or 90%, changing how long you're on, that's the modulation. And what's great is you can send out an analog signal with only one pin. All right. But because look at the thing in red here. It goes from 0 to 1 and back to 0. So just looking at it, you know that there is a DC component to the Fourier expansion, right? Now, it might, by now you should be able to think, you know, that looks like it's 50% on, and it's probably 90% chance that any square wave I show you will be a 50% duty cycle, right? So what's A naught? Right? It's a half. And so there it is in time, right? And then here's what's changing in time, right? Minus 500 millivolts to plus 500, right? And the whole point of this is to keep the DC. Now, here's the thing. Yes, we are changing the duty cycle in time, right? Because, you know, if this is a music player, music changes in time. But so it's kind of like you're keeping the DC part, even though that might change over time. So in a way, it's a trick, right? Because this signal doesn't exist for all time. It just exists for long enough, right? What's long enough? Well, for a low pass filter, 5 tau, right? So we have to get rid of this part with a filter and keep that part. That means low pass. Right. So again, just looking at this intuitively, what fits into this square wave the best? Right. Well, a sine wave. Now, sure, over here it's underestimating it, and here it's overestimating it. But you know, that's just a Fourier transform of two things, right? You have expansion, you have the DC offset, and you have one sine wave, right? So how can we calculate what would happen if we have a 10 kilohertz sine wave with a magnitude of 0.5, right? And we've done that before, right? I come up at 10 kilohertz, I come over here, the gain is -7, right? That my linear gain is 0.44. And so my output is 0.4467 times the original magnitude times, you know, whatever this, you know, that's the sine wave, right? Now I've left out the fact that there's a phase change here, right? And you can see that V in is higher and V out is lower, and it's delayed, right? So I didn't put in the phase, but in some ways, phase is a matter of what you're looking at. All right. So now let's look at this pulse width modulated signal when it's filtered, right? So this sine wave is the sine wave that we calculated over here. Okay. This output is when that's the input. And it's like, well, what's going on? I thought I was going to get a sine wave, right? Now I'm getting like some kind of weird triangle wave, right? And that's because by now you're probably already thinking I'm dragging this out. is that even though there's a fundamental frequency of one sine wave here, there's an infinite amount of sine waves that we have to sum up, right? This is the first one, but then we need the third, fifth, seventh, ninth. And I think in the lab manual, I took it out to 50 terms before Scopy couldn't really measure the difference. All right. And so even though you might have a gain bandwidth of an op amp of 1 megahertz, right? Divide that by 50 to get like the maximum square wave frequency so that you don't get the harmonics. Okay. So meaning if I had a square wave at 1 megahertz, right, not only would it wouldn't work because the fundamental frequency would be at 1 megahertz, right, if the gain bandwidth was 1 megahertz, but it's got all those extra frequencies on top of it. And so, yeah, even though these are efficient on pins, square waves come with a lot of higher harmonics. Okay. So now what we can do is just move our filter around and have a different filter, right? And so so how do we get rid of those harmonics? Well, you could right, if I'm trying to filter 10 kilohertz, well, move this whole filter to the right, and then it'll filter more of it, right? Or we can make this line sharper with a higher order filter, right? And the one we use in lab is the Butterworth filter. So by changing the filter right now, I'm getting this. Now the output of the pulse, the square wave entering this low pass filter is still looking triangular, and I'm just giving the sign as a reference. All right, but this is just intuitively like what's going on. All right. Now you can make a second order filter out of resistors and capacitors, but they're kind of difficult to analyze. But this one, right, this is attenuating frequencies at one rate. This is attenuating them even higher. And you can see that the ripple is even smaller. All right. And what is that ripple? Right. Well, as I said before, the digital value is depending on how long you're on. Right. So, well, I might be able to control how long I'm on, right, which gets converted to a DC signal. There'll always be that ripple there. So if my ripple is 0.5 volts, right, I can only go in steps of 0.5, right, because the 0.5 ripple will wipe out whatever I'm trying to do. So the smaller that ripple, the better. Now, what's great is that the 50% duty cycle has the largest ripple. So if your ripple is 1 millivolt at 50%, all the other ripples will be smaller than that. So you actually only have to test 50%, which makes it really fast. Okay. So now here's a better picture of, so this is, I'm on for an eighth, right? I'm on for 2/8, 50%. And essentially, this would be the analog voltage out. So if this pattern is repeating where I'm on for an eighth, I'm going to get an eighth of the power supply, right? Then I'm going to get here, I'm going to get a half of the power supply, and so on, right? But each one of these is repeating. So if this is repeating for a long time, I'm going to get this value. This isn't really, even though this is in time, down here is not in time. All right. So if we're going to make a pulse width modulated DAC, what's the highest pulse width modulated frequency we can use, right? And that's whatever the clock frequency is of the chip. Now, in this case, right, you've got to be able to divide up the clock of the chip into values. So if I'm at 1 megahertz and I have a 500 megahertz frequency of my pulse width modulated signal, I can really only have 2 values because it can only count, right? And so because of this, the smaller the clock frequency of the pulse width modulated DAC, right, the more bits I can get out of it because there's more things I can divide it into, right? And I'm going to jump to this right now. But on the other hand, you're having to filter that out, right? And so we have, this is the upper limit for the clock. This one's the upper limit for the filter. And notice they're going kind of in an opposite direction. So you kind of sum them in parallel. And right in the middle is the maximum number of bits you're going to get and the frequency that you'll get it at. All right. And the rest of this is more for lab. All right. And we just got other things to do that I have to. All right. Now, the Butterworth filter, right? What it does is that the higher the order, the sharper it is. Now, why are these lines not straight? Why are they kind of curving? That's because this is a linear axis. All right. And the higher order the filter, the sharper it becomes. But the longer it takes your signal to propagate through the circuit. All right. And the thing is there is an algorithm to help do that. And really, it's all based on the unit circle. Okay, so if I have one root here, right, that's omega naught S plus omega naught, and it's a low pass filter. And you can have Butterworth high pass filters, right? And so in fact, this is a Butterworth filter with n equal to 1. But then, and I'm just going to, I'm trying to draw a half unit circle here. Excuse me if it's not. All right. Well, what if I wanted a second order Butterworth filter? Well, the radius is 1, right? So I'm getting S plus 1, no, sorry, 0.707 plus 0.707 J. That's one pole. And then I get its complex conjugate. All right. And then if I wanted to do 3, right, it would go here, and then I'm trying to split it so that the angles, these angles would all be equal. And then a 4th, 1, 2, 3, 4, right, and so on. But whatever it is, you're distributing the poles along that circle, okay? And so the Butterworth thing is just you arrange these poles, however many you have, on the unit circle and keep them the same angle apart. And when you do that, you get this. Notice how there's no overshoot, right? Like here, there's like an overshoot, right? But here, this is an actual like Bodie plot, right? Notice that it just gets sharper and sharper. The bandwidth stays the same, and it just gets sharper and sharper and sharper, but there's no overshoot. Where some of these other, and here are the constants, right? I think here, there's other filters, right? And this is on the linear scale that have an overshoot, right? Eventually the Butterworth goes to 0, right? But some of these other ones don't, but you can tell that they're sharper, right? So you can choose any one of these for your project. Python allows you to set it to whatever you would like. Okay. So this is to help you. This is a link to lcopy. It's another thing in Python, and it's just a file that will print out your poles and zeros. So here, there's a pole at 0, right? But then there's a pole at plus or minus j omega. And then there's a 0 here on the left-hand side and a 0 on the right-hand side. Now, in the homework, I'm asking you to come up with your own algorithm, okay? And here's one, right? I start off here, and I'm just taking a linear line back. And this is at a half, this is at a half. So everything, this is 0.5, 0.5, 1, 1, 1.5, 1.5. The part of the thing of the homework is you come up with your own pattern, right? In the homework, I give you another sample pattern and you can just follow that process. I would suggest doing it for the low pass because that's easier to understand, all right? But this one pattern, not the one I showed you there, but I have all my roots, my poles, right, scaled. It looks like I'm going by, 3/4, 1/2, 1/4, and it's giving me my complex conjugates, right? And then I programmed everything into the behavioral of LT Spice, right? And even though time domain from Laplace is difficult, that's essentially a low pass filter, right? Here, if we now and there's the Bodie plot. So there's no overshoot, right? I'm not saying I invented any great new filter, but you can come up with your own pattern. So it's a chance to really be creative. Okay. It's more, just don't give the one that I did, right? That's all you got to do. All right. Now, So this is just an animation, and I'm just changing, it's a low pass filter, and I'm just changing the damping ratio, right? And you can see that you have a peak in the gain, and then it gets smaller and smaller, and you can almost see two break frequencies, right there. All right. But this is a Bodhi plot version of this. Okay. Now, something is, what would that look like on a linear? Oops. What would that look like on a linear scale? Or, well, actually, it's still in dB, otherwise it doesn't work. But there's something that we don't talk about much, is that in the Fourier domain, we actually have negative and positive frequency. But in the Bodhi plot, we only do the actually, this is it's linear, it's not in dB. Otherwise, it would look like a Bodhi plot. So really, this is both sides. And if I only took this part and excluded 0 and took 20 log of it and put this on a log scale, I'd get back the Bodhi plot. And sometimes in modulation, you need to talk about the fact that there's this negative and positive frequency. All right. That was now, this is my attempt to try to link the S domain to the frequency domain. Yeah, the S domain to the frequency domain. And so this is the complex plane. Right here is where the real part of the plane is 0. Okay. And over here, you can see these going up, right? Well, that would be the poles, right? And then here, no, wait, going up, yeah, going up is a pole, and going down are some zeros. And pulling up on this grid does one thing, and pushing down on a grid, but by carefully selecting them, you're getting the Bodhi plot, where if I rotate it like this, oops, and now rotate it up, okay, I'm just gonna, and take it from 0 onward, this is the notch filter. You don't see this, right? Because we set S equal to J omega. All right. And we have one last thing, I think. So here we have two poles, right? Because the pole is where it goes to infinity. So if I rotate it like that, like straight at you, it's hard to control. All right, these things coming out, right, would be I guess it. Right, this is the complex plane. Here's the real, here's the imaginary, and there's two poles, right? That means this is going to infinity right there, if it was in 3 dimensions. And so, yeah, that's coming out towards infinity. And then if I rotate it back to you, okay, right here is 0. So there's no real part. And if I just got rid of the negative frequency and plotted here, you would see that Butterworth filter response. All right. And hopefully that helps you explain, link the two. All right. Now, oh, that's the research project. So I want to make a clock with the power from the wall. Okay. Now, this is the United Kingdom power, so we're at 50 hertz, right? I take the whatever the RMS is and multiply it by the square root of 2, and that's giving me my amplitude. So this is the wall coming out of the power, and I want to run a clock off of that. All right. Now, at 155, this voltage is a little bit too high for normal components, so we want to bring it down. Now, if you said, well, I'm going to use voltage division in 2 high powered resistors, okay, that'd be okay, right? But it is better to use a transformer, right? And so these windings are set so that now and if I want to see the differential power, right, voltage, I just put a comma, V minus. All right, so there's my sine wave, right? Now I'm at 12 volts. All right. So all that is a transformer. Again, you can decide how you want to do that. And again, I've gone and done like a much more detailed solution than you would have to do in the homework. All right. Now, we've got to convert this sine wave into a DC signal, meaning it only goes in one direction. DC doesn't mean it's constant. It just means it doesn't go negative. All right, one way is to take the absolute value, which is what this one does. And the other way is to use this full wave rectifier. All right. So now, right, if I were to do the Fourier expansion of this, I'd say, well, A naught is 0 because it's averaging to 0. And then I'd find the peak and call that the magnitude. And then I'd know the frequency and I'd have there's only is 2 terms. Here, right, well, it's doesn't go negative. So the areas never cancel out, right? So there will be some DC component, and that's what we're actually going for. And then there's these higher frequency components, which we can just take by looking at the, and let's look this at a linear scale. Okay, which we can just take and say, oh, there's something at 100 hertz, 200, so on and so on. You can see the peaks, right? Now, the DC part that I said existed, the Fourier transform gets rid of that, or at least LT Spice does. These are the signals we want to get rid of. So if I want a low pass filter to get rid of the AC signals, it's got to be attenuating at least before 100 hertz. Okay. So one way to do that is a low pass filter. All right. Now, why is it taking time to get up to be a sine wave? Well, because LT Spice really is a Laplace type simulation. The signals don't always exist for all time, right? Now, here's the thing. This signal is rising, and eventually, right, it will exist for all time. And if I run the simulation for a little bit longer, Actually, I don't want to do that. But if I were to just zoom in here, oh, there's my sine wave, and it's always been a sine wave. Okay, so so eventually it'll get to wherever it's going, halfway, right? Now that is a DC signal, right? But it's still got a ripple in it. Now, mathematically, the absolute value is very efficient way to take it, but really you have to use a full wave rectifier. Okay, and it's taking time to get to go where it's going. Also, it's also attached to the low pass filter so that these things are not independently connected. So by attaching the low pass filter to this circuit, it's actually affecting how it works. All right, so if I look at L2, okay, here we're getting our DC signal eventually. Now, this is like the bonus. If I were to change the load here, that 100K is the load, right? So if I put in a different resistance because I'm powering something else, it changes the whole filter characteristics. And you don't want that to happen. So what you do is you use a linear dropout regulator so that no matter what the voltage is here, this, and essentially it operates like an op amp, right? But what it does is it sets the output voltage to kind of a fixed value and just takes this as power. So if we look at that, it's oscillating. And once it gets to a certain value, there's our DC supply. All right. So really, we had these frequencies, and notice it's at 100 because taking the absolute value or using a full wave rectifier doubles the frequency. We got rid of these with a low pass filter, but it had a time constant, right? So it's taking 5 tau to reach wherever it's going. All right. This isn't 5 tau. That's just the output reaching what it needs. 5 tau would be, you could calculate what 5 tau was, right? But the smaller the cutoff frequency to get rid of more high frequency harmonics, the longer it's going to take for your power supply to react. Now, how can we get a clock signal out of this, right? Well, I have, again, reduced using the transformer. Instead of 155 volt sine wave, I'm getting around 12, right? Again, you could say you're using voltage division, but really this is better. And so this is going into this buffer, right? Powered by this power supply, and it has a gain of 1, right? But what's the power supply? It goes from 0 to 2.5 volts. Okay. So this can't go above 2.5 volts. And so I'm bringing in a sine wave, but as soon as it tries to go above 2.5 volts or below 0, it just stops. And so there's my so it takes a while, right, to get going, but there's a clock signal that can be used to drive whatever digital circuit you want. All right. So even though, right, this is a power supply project, kind of using the Fourier expansion to set the filters and make this work. And on the final exam, I usually have some kind of example where I ask something like this. Now, because it's like a question you probably never have seen before, I'm really thinking more for thought process. You wouldn't have to give me a schematic like this, but actually this is almost a homework question in EE 134. But this is very simple compared to what you're learning for power supplies there. Okay. So I've kind of told you how to answer that one, but I really want you to do it in your own words and in your own thoughts. And yeah, you can get as creative as you like. Okay. So this system is out of control, right? Now, yeah, you could, it's not enough just to say the S term is missing and this is negative. You really have to use the quadratic equation, right? And so B right? B is missing, right? And so we have plus or minus -4 times 1 times -7. You know, I'm going to change this. Okay. And so this becomes plus or minus the square root of 16 divided by 2, which equals +2 and -2. This root here on the right-hand side will make some kind of exponential increase, which is why it's out of control. Now, how do we fix it? Now, in the fixing, knowing, oh, you know, I got to change the sign of this, and there's an S term. Oh, no, that's very helpful, right? So we just put this into the QS form. Okay. And yeah, now, how do I turn? I have to turn G of S times S squared into, you know, something like that. How do I make that happen? And then I have to turn G of S times -4 into some positive number. All right. So let's do the easy one first. I guess G of S -4, G of S, right? When I multiply that, it has to be greater than nope, sorry, that's a plus sign there. G of S minus 4, right, times S squared, right, has to be greater than 0, right? So that means S squared G of S. Okay. Now, what is going to turn this into a constant, right? Well, you always have to have some kind of constant, right? But how do I do that? Well, the only thing that's going to make that work is K divided by S squared, right? So the first part of G of S is going to equal K. And since there's going to be more than one thing, I'll just say 1, right? And that K1, right, has got to be greater. It's got to be greater than 4. This isn't right. Okay. K1S times S squared divided by, okay, minus 4 has got to be greater than 0. So these cancel. What makes that greater than 0 is when, oh yeah, I should have had a plus 4 there. K1 has to be greater than 4. That's the first part. But now then there's a second part, right? That G of S times S squared, right? Well, there's nothing there originally. It's not negative or positive, but we got to turn it into something times S, right? Well, what's going to convert this into something times S? Well, the only thing will be K2 divided by S times S squared, right? And in that case, K2 just has to be greater than 0, all right? All right, K1 greater than 4, K2 greater than 0. And that would be the complete excuse me, the complete solution. All right. All right, so this is today's breakout room activity, right? Find out why it's out of control, then put it into the QS form, all right? And then design the GS to make it in control. And then what are the conditions on that? Okay, so I will break you up. Okay, let's pick up. where we came from. So it's a very similar problem. The only thing is that we have s instead of s squared, but we still have our term in the middle. The s part is missing, and we just have a different negative issue number. So we really get plus or minus some real number, and that real number gives us an exponential increase. All right. Now, how do I turn s into s? Well, you just scale it by a constant, right? And so k1 just has to be equal, greater than 0. How do we turn s into a constant? Well, multiply it by an integrator, right? And now, because there's an 8 there, a minus 8, it has to be bigger than that, right? And so I didn't really that's q of s, right? And that's the g of s to get that to be fixed. Okay, so that's that might have been a little bit quick, but it is recorded. You can review it at your leisure. I know you have to go to 112, right? Again, today might have seemed a little bit like it was all over the place, but it really was review of some things on the midterm and trying to look at the world through the Fourier expansion. And, do I want a DC? The power supply, we're trying to get a DC signal. The pulse width modulated DAC, we're actually going for a DC signal. All right. And we're trying to link how the poles in the which are represented in the complex plane affect the frequency domain, which is when the real part is set equal to 0. All right. And it should provide you with more information to help you kind of get a feel for what's going on. But if some of those animations were too confusing, that's not really on the exam. I'm trying to give you a deeper understanding of what's going on. Okay. All right. Take care.
All right, have a good day.
You too.